So, we are going to look at models of electrical double layer. Okay. So, I am going to start with the simplest model. It is what is called as Helmholtz model. Okay. This is one of the first models that was put forward, and so in this case what is thought of is the counter ions. Okay, they are directly bound to the surface of the. So, if what you are looking at is a picture where you have a solid surface. Okay, it could be, you can think about it as a part of a spherical particle. So, I could look at a spherical particle. I am only looking at a small portion, right. That is a solid surface. Okay, that is a particle of interest, it could be. Okay, and these are the charges on the particle surface. These are the counter ions, right. Okay. So, in this Helmholtz model, what is assumed is that the counter ions are directly bound. Okay, they are directly bound or attached to the particle surface, and they neutralize the charges on the surface. Okay, they neutralize the charges on the surface, giving an arrangement which looks more like a capacitor. Okay, so, capacitor, you can think about two plates, right. Okay, which are oppositely charged. Okay, so, that is a capacitor like arrangement, right. So, in this particular double layer model, it is assumed that the counter ions directly bound to the surface, and then they neutralize the surface charge and give you some kind of a arrangement which looks like a capacitor. Okay. Yeah, this point we will come back to it later. Okay. So, what is mentioned here is the electric field generated by the surface charges in such a system is limited to the thickness of a molecular layer. That I will come to this particular point a little later. So, what is shown here is two arrangement, okay, like a capacitor like arrangement. So, I have a charged plate. Okay. So, this could be the the plate that is because of the counter ions, right, in the solution, and that is the charges. You can think about this as the charges that arise because of the particle surface. Okay. And in case A, you have vacuum between the two particles. In case B, you have some medium, okay, which will be the case if you look at colloidal particles in solution, you will always have some medium, right, between the two layers. Okay. And so what we are going to do is we are going to use a concept called line of forces, okay, which you would have seen in electrostatics, right. So, you say that if I have a charged plate, okay, say that, some there is a positive and negative charges on the surface, right. You talk about the lines of force that start from a negative charge and they go to the positive charge, and they can continue, right. So, we are going to use a concept like that, right. So, the lines of force that start from one charge surface, okay, they start from one charge surface and they terminate at the other charge surface. Okay. And if you assume that the particles, the surfaces have a area A, suppose that the plates are of area A, and if the total charges that each of these plates carry is Q, then we can define a quantity called the surface charge density, okay, which essentially is the charge per unit area, right. I can define that. This is the surface charge density sigma star, which is the total charge divided by the area of the plates, right. Now, what you can do is that, so since a line of force, okay, is associated with each unit charge, okay, for every charge that you have there is going to be a line of force. Okay. So, because you have a charge density Q by A, okay, I can say that there are Q by A lines of forces that cross from one the charge plate to the other charge plate. Okay. And therefore, you can say that this E naught, that is the electric field, okay, that is arising because of q by A lines of forces, is q by A divided by 1 over epsilon, right. So, that is in a way this tells you what is the force. See, this is q by A is the number of lines of forces, okay, and the electric field generated is proportional to the number of lines of forces. And of course, you have to take care of the effect of the medium between the two plates. In one case, the medium between the two plates is vacuum, therefore, you have 1 over epsilon naught. In the second case, when you have a medium dielectric medium present, this factor you are going to replace that with 1 over epsilon naught into epsilon r. Okay. So, in essence, this epsilon r and epsilon naught tell you something about what is the electric field that is generated because of the two arrangements which are shown here. Okay. So, if you look at this expression, right, this is very similar to what I was mentioning about. So, we had mentioned that so in a way, okay, we will come back to that point. Okay. Now, so now I would have to relate this is the electric field. Okay. You will see that in Colloids literature, when people work with charged particles, okay, you will always see that say it turns out that for getting working equations for like say the interaction potential, for example, phi electrical double layer interaction, you will see that the such the expressions that deal that concern electrical double layer interactions, they are always represented in terms of the surface potential. Okay. You do not see the charges directly in the expression, but you will see that all the equations have the psi, which is what is called as a electric potential. Okay. And that electric potential is related to the electric field that is generated because of the charges, okay, and which in turn is related to the charges that are associated with the particles. Okay. And this electric field E is given as negative gradient of the electric potential. Okay. So, therefore, what I can do is if I assume that the drop in the potential is very small, I can replace d psi by delta psi, and this dx is the distance over which the potential is the distance over which the potential is changing, and this delta, okay, that is a distance between the capacitor plates, okay, and that will be equal to sigma star divided by epsilon naught into epsilon naught. That is for the case where you have a medium of epsilon is a dielectric constant of the medium between the two plates. Okay. Now, to show that, so now I will come back to this point, right. We had mentioned that the electric field generated by the surface charges is accordingly limited to the thickness of a molecular layer. Okay. Just to make that point, what I am going to do is to calculate few. So, this is in essence what is the capacitor model. Okay. So, if you have you could have a positively charged plate, for example, and negatively, this is the charges on the particle surface, okay, and this could be the charges in the counter ions, right. These are the ions which are tightly bound to the charged surface, okay, and that is the distance delta, okay, and this psi b minus psi alpha is the potential drop, okay, and you can do some simple calculation. I have taken a case where you have a, so let us think about a simple case where I have a charged surface, and imagine that this is a charged surface which is because of a surfactant molecules, okay, which are attached to the particle surface. Okay. Now, if the charged monolayer, so I am talking about monolayer because I have a single layer of surfactant attached to the particle surface. If the charged monolayer has an area which is 10 nanometer square, okay, a charged monolayer of area 10 nanometer square is what I am considering. Now, if you, okay, for a monovalent ion, this corresponds to a charge density. So, what you can do is say that I have a 10 nanometer square area, and I have one ion per 10 nanometer square. Okay. If I have one ion, the charges on the ion is going to be 1.6 into 10 power minus 19 coulombs per ion. Okay. Therefore, I can get a charge density, right. So, you should imagine that I have a monolayer of surfactant, okay, and if I say that there is one ion for every 10 nanometer square area, okay, for every 10 nanometer square there is one ion present, then the charge density is going to be one ion per 10 nanometer square. Therefore, this number becomes 1.6 into 10 power minus 19 coulombs divided by per ion, right, that is a charge per ion, right. So, therefore, you get a sigma star which is 1.6 into 10 power minus 2 coulomb meter square, coulomb per meter square, right. And you calculate epsilon electric field, okay, that is sigma star, right. We go back here, sigma star. So, I plugged in sigma star here, okay, 1.6 10 power minus 2 coulomb meter square, and epsilon naught, right, that is your epsilon naught, and that is epsilon r. Okay, therefore, your epsilon E epsilon becomes 2.26 into 10 power 7 volts per meter, right. And typically when people talk about charged surfaces, typical potential drop are of the order of 0.1 volts, okay, or 100 millivolts, okay, that is a typical potential drop people talk about. So, if I substitute for delta del epsilon, okay, or the change in the drop in the potential, I can get delta, and the delta comes out to be 4.4 nanometer, okay. So, therefore, you can say that because we are assuming that the counter ions are directly bound to the particle surface, and typical the thickness of the double layer one can think about is of the order of 4.4 nanometer, okay, in this particular example, okay. Therefore, in the capacitor model we should assume that the electrostatic interactions, okay. So, in a way this tells you something about the range of distance over which the electrostatic interactions are operative, right. Can I make that statement? This, so what we are saying is that if you look at this particular picture, right, that is a charged, okay, that is a charged surface, okay, and we are saying that the surface charges are bound to the counter ions are bound to the particle surface, they are strongly bound, in essentially neutralizing the entire surface, okay. And because of the fact that they are strongly bound, we can imagine that the electric field that is generated by the surface charges would be of the order of molecular layer thick. That is what we kind of proved by looking at some typical numbers of the delta that we get for a particular case, okay. So, maybe just go back and take a look at this again, maybe we will discuss this example again in the next class. Okay. So, the first simple picture that we looked at is Helmholtz model, but the more realistic picture is that the such a strong binding that is kind of assumed in the electrical in the Helmholtz model is actually not completely true. Okay, that is because the counter ions that are there in solution, they are also free to move around, right? They also have thermal energy, right, kT, and because of this thermal energy they can also go away from the surface. Okay, and then you get a kind of a distribution which is not exactly like a capacitor arrangement. Of course, there is going to be a larger concentration of counter ions close to the surface, but the arrangement is not exactly like a capacitor kind of a concept. Okay, we will try and talk about it in the next class. Yeah.